Okay, so my plan here is to give you an alternate solution from the textbook solution on problem 1.1.3. I want to use the non-SI units, so we're going to focus on milli-electron volts here. And I'm also going to showcase a equation or a problem-solving technique I call equation mapping. And so let's just get started and see how this works. So in this technique, I read the problem, and it says an electron with a center wavelength of 10 nanometers is accelerated through a potential of 0.02 volts. What is its wavelength afterward? So the thing I'm going to start with is the objective. So I'm going to underline that. And once we know, okay, that's where I'm going to start. We're going to look for the final wavelength. I'm going to write an equation that has that in it. And one equation we have is that there's a momentum that's equal to the Planck constant over the wavelength. And just to indicate that we're talking about the final quantities, I'm going to put the subscript F. Now, what we're looking for here is lambda F, so I'm going to circle it. I'm going to put a check mark by everything we know. We know H. That's a constant. And now I'm going to put a box around this final momentum because we don't know that. So we have one equation, two unknowns. We need to bring another equation in to solve this. And so another equation that we can bring in, something that will help us to solve for the final momentum, well, let's say, let's use kinetic energy. And so the kinetic energy at the end of the process is equal to the final momentum squared over 2 times the mass of the particle, which in this case is the electron. So again, in this case, we've moved on to a secondary equation, and now in this secondary equation, we really need to solve for this PF, the final momentum, so that we can plug it in here. But we know that the electronic mass is a constant, so we're going to give that a check mark. And at this point now we need the final kinetic energy. Okay, so now we need a final kinetic energy, and we know that the change in kinetic energy is well, it's 0.2 volts, and we're dealing, or 0.02 volts, and we're dealing with 1 electron. So we want an equation maybe that has final kinetic energy and a change in kinetic energy, and we can do that if we say, okay, the final kinetic energy is equal to the initial kinetic energy. Let's just make that better for a second. Initial kinetic energy plus whatever change in kinetic energy that we have. Now, again, let's see, now we need to solve for the final kinetic energy, so we can plug it in here. And in this problem, we know the change in kinetic energy, but we don't know the initial kinetic energy. However, we are given this condition, that the center wavelength is 10 nanometers, and this is at the beginning. So now we need to bring in one more equation to help us calculate the kinetic energy at the beginning. So we'll say the kinetic energy at the beginning is the initial momentum squared over 2 times mass of the electron. And let's see here. I guess let's just go through this again. And we know the mass of the electron. We need the initial kinetic energy, so we can plug it in. And now we also need this initial momentum, but we can get that if we use the equation P I equals h over lambda I. That's again, that's De Broglie's relation, and we're going to say, okay, well, we know the initial wavelength, we know Planck's constant. That gets us the initial momentum, which is enough to get us that. And now you can see that there's a process. We've got everything we need to get at the end of the problem. So it now becomes a plug and chug, and I've outlined the problem. I've given you and me a map to solve the problem. So let's just do some calculations here really quick. Starting with some physical constants, I'm going to write down here things that are given. So let's say the mass of the electron is 0.511 mega electron volts divided by c squared, where c squared, or c, let's just say c is the speed of light, and it's 2.997 meters per second. And we also need h, Planck's constant, which I like to use electron volts. That's 4.136 times 10 to the negative 15 electron volts times seconds. And so we can just get at it here. So we can do the math, and for pi, initial momentum, I get 4.136 times 10 to the minus 23rd, and we need the units, and those are electron volt times seconds over meter. So I just I took the c squared, no, I'm sorry, I just took the h and divided by lambda I, initial wavelength. Okay, so I get that for pi, and then I can then use pi, and I will calculate that the initial kinetic energy, if I do the math, I get 15.03 milli-electron volts, and that is that's the initial kinetic energy. And then if I can take that and I add that to the, let's see, we're given it's 0.2 volts. So that speaks of 0.02 electron volts, because we're accelerating an electron through that, which is the same as 20 milli-electron volts. So now we know then that the final kinetic energy is, well, let's just say that's 35 milli-electron volts. And then we use that, and we're going to get the final momentum. And when you do the math and you track the units on that, you're going to get that the final momentum is 6.31 times 10 to the minus 7 electron-volt seconds per meter. We'll label that as final momentum. And then, doing the math, once again, we're going to get that the final wavelength is 6.55 nanometers. So I didn't show the numerical steps, but I did give you a map that shows you exactly how to solve the problem, and that is the equation map technique, and we're using the non-SI units, which actually for problems in quantum mechanics are easier and more straightforward than converting things to SI units, in my opinion. Thanks for watching.